In this video, we're going to be talking about the differential distribution table of an S-box. This is a table of contents of this video. First, we'll just provide some motivation of why we'd want to study this object. We'll review sequences of bits, the XOR operation, some properties of XOR, and then we'll talk about what a difference set is and what a different set of an S-box is. And then we'll be able to define the DDT, the differential distribution table of any S-box. We'll talk about the properties of the DDT, and we'll relate the DDT to probabilities. Then we'll calculate the DDT of a linear S-box, the DDT of an XOR S-box, and then we'll write some code which can calculate any DDT. And then we'll look at the differential distribution tables of some interesting S-boxes that are used in real-world ciphers like DES and the Rijndael S-Box that's used in AES. So let's first just talk about some motivation of why we're going to study this object. If we're given an S-box, which goes from sequences of n bits to sequences of m bits, call that S-box S, we want to define an object called the differential distribution table of that S-box S. And we denote it D or D sub S. And differential distribution table we're abbreviating as DDT. And what is this table, or a matrix if you want to think about it like that, but we'll just think about it like a table. A table has rows and columns. So this table will have 2 to the n rows and 2 to the m columns. And the entries of the table will all be non-negative integers. And non-negative means 0 or positive. There'll in fact be a lot of zeros in our table, but there will be also positive integers in our table. And this table is called the differential distribution table, the DDT, of the S-box. And we would just like to provide some motivation of why we would want to study the DDT of an S-box. So communications over public networks are kept secure through encryption, and this encryption is achieved through the use of a block cipher encryption algorithm. An attacker, he would seek to discover a vulnerability in the design of a block cipher. And he would hope to do that in order to know the original plain text associated to a given encrypted ciphertext. Analyzing cryptographic systems like block ciphers for weaknesses, for vulnerabilities, is called cryptanalysis, and the practitioner is called a cryptanalyst. There's many ways of attacking a block cipher, and one is called differential cryptanalysis. If you were looking to attack a certain block cipher through differential cryptanalysis, the very first thing you would do is calculate the DDTs of any S-boxes that are used in the design of that block cipher. In all block ciphers, you're going to have S-boxes, and you would look at the S-boxes individually, independent of the whole cipher, and just calculate the DDT of those S-boxes and take a look at them. So we view calculating the DDT of an S-box as the very first step in designing a differential cryptanalytic attack on a block cipher that uses that S-box. And we won't talk about differential cryptanalysis in this video, but we hope to do soon in another video. So how does the DDT of an S-box reveal potential vulnerabilities of a block cipher that uses that S-box in its design? Well, if the DDT of an S-box contains a large integer value, a large positive integer, that's a sign that it may be vulnerable to an attack by differential cryptanalysis. If the DDT of the S-box only contains small integers, then it's very much less likely that the block cipher will be vulnerable to an attack by differential cryptanalysis. Let's also note that there is an analog to the DDT found in another method of attack called linear cryptanalysis. And there we first look at the linear approximation table, the LAT, of each S-box used in the design of the cipher. So a LAT would be the first step in looking for an attack by linear cryptanalysis. Calculating the Ddt of S boxes is the first step to design an attack by differential cryptanalysis. Let's let F2 be the set 0 and 1, and it's just a set of bits. There's only 2 bits. And by a sequence of bits, we just mean a sequence of zeros and ones. And if we have a value n, F2n will be the set of all bit sequences of length n. We can think of those as n tuples, x1 up through xn, where each xi is in F2. So clearly F2n has 2 to the n elements. And if we regard these as bit expansions of integers, we can think also of F2n as a set of normal integers, 0 up to 2 to the n minus 1. Now let's also recall the XOR operation. The XOR binary operation on F2, we write that O plus there. And here's the table of values that describes this operation. And really, it's just like addition modulo 2. Here, when we look at the table of values, they're all pretty obvious. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1, we'll say, is 2, but 2 modulo 2 is 0. So that's the intuition behind the XOR addition operation on F2. And we can actually extend the definition of XOR to not just be on F2, but to be a binary operation on F2n. So if we're given 2 sequences of n bits, say xi and yi, to XOR those sequences, we just XOR the individual components, right? x1 XOR y1, all the way up to xn XOR yn. And why do we use notation 0 sub n, 0n, to note the element of F2n, which is all zeros? So it's kind of like the 0 vector. Now the properties of XOR, let's just review some of those. These are just some standard properties, and they hold for all elements of F2n. So x XOR y is the same as y XOR x. That's commutativity. The next one is associativity. The next one is the statement that 0 is the additive identity. X plus 0 equals 0 plus x equals x. And then we have x plus x is 0. That's an important result. If you add x to itself, you get 0. And that kind of means x is its own inverse. So this is an important little thing as well. Subtraction is the same as addition. We'll talk more about that in a bit. And then the second last one there says that if x plus y is 0, then x equals y. That's really, if we combine the fourth and the fifth point there, we could say x plus y is 0 if and only if x equals y. That's a nice way to look at it. And then the last one, if you wanted to solve a linear equation, a plus x equals b, then x is just a plus b. So these are all very easy to prove, and let's move on. And as we saw, this operation provides the set F2n with the structured abelian group, and it has the identity element being 0n. And like we mentioned, since x plus x is 0, we see the inverse of any element, negative x, is x with respect to this operation. So that means that in this abelian group, subtraction is the same as addition. And with this in mind, let's just make this definition that when we say the difference of 2 elements in F2n, let's say we have x and y in F2n, the difference of those elements is defined as x plus y. So maybe that's a little bit odd to define difference as x plus y. But since subtraction and addition are the same in this abelian group, it's just common to do that. Normally, we would call x plus y the sum of x and y, right? But in the context of DDTs and differential cryptanalysis, it's standard to refer to x plus y as the difference of x and y. Okay, so let's look at this important definition, the difference set. If we fix an element alpha in F2n, Let's define the subset delta alpha of the product F2n cross F2n by the set of all ordered pairs x1 and x2, where x1 plus x2 is alpha. In other words, the difference of x1 and x2 is alpha. So delta alpha is just a set of ordered pairs of elements from F2n which have a difference of alpha. And we call that the difference set of alpha. Now we have a simple proposition we can prove right away that for any alpha in F2n, the difference set delta alpha contains 2 to the n elements and can be kind of parameterized by delta alpha being the set of all ordered pairs x comma x plus alpha, as x is a free-ranging variable over F2n. So it looks like for delta alpha, the first component can be anything, and then the second component is determined as the first component plus alpha. And this is easy to prove. Why don't we just give a detailed proof though? Let's define S to be that set of ordered pairs x comma x plus alpha. And our goal is to prove that delta alpha is equal to S. One common way to do that is to show that each one is a subset of the other. And if that's the case, then equality would have to follow, right? Let's say we have an ordered pair x1 and x2 in delta alpha. What does that mean? It just means that their difference is alpha, right? x1 plus x2 is alpha. Now, by the properties of XOR, we could kind of just, why don't we think of adding x1 to both sides to this. When we do that, x1 plus x1 here is 0, and we're just left with x2. And this side, we'd have alpha plus x1, or x1 plus alpha. And it looks like x2 is of the proper form, right? x2 here, the second coordinate, should be the first coordinate plus alpha. And we've proven the first subset, that delta alpha is a subset of S. Now our goal is to prove the other inclusion. So why don't we take a member of S, and that means that it's of the form x comma x plus alpha for some x. And why don't we just observe that if we add the two coordinates, x plus alpha, we get, well, those x's cancel away to 0, so we just get alpha. And it looks like when we add these up, we get alpha. So by the very definition of the difference set, this ordered pair has to be in it. So S is a subset of delta alpha. When I combine the facts that both of these subsets exist, it necessarily proves the equality of the sets. That's just a standard technique of proving two sets are equal. And since F2n has 2 to the n elements, and x is the first element of these ordered pairs, then delta alpha must also have a cardinality of 2 to the n. Maybe the abstractness of the proof makes it look more complicated than it is, but this is the first thing to observe, that the set of all ordered pairs which have a difference of alpha can be parameterized by x comma x plus alpha. Of course, you could put the x in the second coordinate, and then the first coordinate would be x plus alpha, but it doesn't matter. So delta alpha is really a subset of the product F2n times F2n. But it is bijective with F2n. And we can see a bijective map very easily. F2n mapping to delta alpha. Just send x to x comma x plus alpha. That's a bijection. And so we kind of understand the set delta alpha. That's pretty clear what that is right now. And why don't we just look at a special case when alpha is 0? So by the last proposition, when alpha is equal to 0, the difference set would be x comma x plus alpha. But since alpha is 0, it's just x comma x, right? So delta 0 would just be the set of all ordered pairs x comma x, where x ranges through F2n. And this set's often called a diagonal of F2n cross F2n. All right, we're finally getting to our main topic here, the different sets of an S-box. So let's just recall that any function S from F2n to F2m is called an S-box. That's, as long as it's a function, we call it an S-box. Let's say we have an S-box from F2n to F2m, and we fix an element alpha in F2n and an element beta in F2m. we want to define the different set of S with respect to alpha and beta by, we'll write delta sub alpha comma beta. It's going to be the set of all ordered pairs x1 and x2, such that x1 and x2 have a difference of alpha, x1 and x2 have a difference of alpha, and then the images S of x1 and S of x2 have a difference of beta. So we understand the difference of the inputs, and we understand the difference of the outputs. And we can also write this as the set of all ordered pairs x1 and x2 that are in the different set of alpha, and the images S of x1 comma S of x2 is in the different set of beta. Just another way to look at it. And when we write it like this, it's obvious that the delta alpha beta, the different set of the S box, is a subset of the different set of alpha. Now, delta alpha beta is always defined with respect to an S box. Delta alpha isn't, right? The different set of alpha is not defined with respect to an S box, but delta sub alpha comma beta is defined. Delta alpha beta is always defined with respect to an S box S. If we ever need to make that dependence explicit, we can just do that by writing a superscript S up here. So just recall that for a finite set X, we denote its cardinality by putting a set of bars around X. And this will be a non-negative integer. It's just the number of elements in the set X. We're going to define D alpha beta to be the cardinality of the finite set delta alpha beta. So D alpha beta is the size of the finite set delta alpha beta, which might be 0, but it might have a positive cardinality as well. And the following proposition just follows from our definitions that D alpha beta, it's a non-negative integer, so it's either 0 or positive, and it's equal to the size or the cardinality of the set of all elements in F2n, such that S of x plus S of x plus alpha equals beta. When we write x and x plus alpha, that guarantees right away that it's in the different set of alpha, right? And if S of x plus S of x plus alpha gives me beta, then it's in delta alpha beta. And the size of that is D alpha beta. Just another way to say it. Let's just look at some specific cases. What if both alpha and beta are 0? Then in that case, delta 0, 0 is just the different set of 0, which is the diagonal that we talked about before. In general, when alpha is 0, the set delta 0 beta is always going to be empty unless beta is 0. And in that case, therefore, the integers d0 beta is going to be 0 pretty much all the time for any beta, except the case where beta is 0, in which case it's 2 to the n. So these are easy to see if you just think about it. And an important little observation is that the integer d alpha beta is always even. And just recall that 0 is an even number, so when d alpha beta is 0, it's still even. Let's just dispense of the case of alpha equals 0. When alpha equals 0, we know that d0 beta is either 0 or 2 to the n, and both of these are even. So we can assume that alpha is non-zero in our proof here. And why don't we also assume that delta alpha beta is non-empty? So there are elements in there. One thing to notice is that if we take any element x1 and x2 in delta alpha beta, then if we flip the coordinates x2 comma x1, that must also be in there, right? The reason that's true is just because of the commutativity of the XOR. And it's also the case that x1 is not equal to x2. And that's because alpha is non-zero, right? x1 plus x2 is alpha. And since alpha is non-zero, x1 cannot equal to x2. And since x1 is not equal to x2 as ordered pairs, x1 comma x2 is not equal to x2 comma x1. So if we introduce a kind of a pairing between x1 x2 and x2 x1, which are distinct elements always, we can partition the set delta alpha beta into subsets, and each subset has a cardinality of 2. And that means the set delta alpha beta must be even. So d alpha beta is always either 0 or a positive even integer. And now we're finally ready to define the DDT, the differential distribution table of an S-box. So why don't we take an S-box from F2n to F2m? The differential distribution table, or the DDT of S, is a table or a matrix. It has 2 to the n rows and 2 to the m columns, and we denote it by script D. We can write an S underneath as a subscript if we want to make explicit which S-box the differential distribution table is associated to. But we usually just write D. So the rows of this table are indexed by the elements of alpha in F2n. In other words, integers from 0 up to 2 to the n minus 1. And the columns are going to be indexed by the elements beta in F2m, which are integers from 0 up to 2 to the n minus 1. And the entry that's going to be found at row index alpha and column index beta is just the integer d alpha beta, which is the cardinality of the difference set associated to the S-box at the values alpha and beta. So the differential distribution table, the DDT of S, is just a table that contains every possible value d alpha beta as alpha and beta range over the rows and columns that we just said. We could imagine it like this. If we have 2 to the n rows here, we have 2 to the m columns. Notice at the very top left, we have 2 to the n. Remember, we said that d00 is equal to 2 to the n. And then the rest of the values in that first row, the 0th row, are zeros after the 2 to the n. And we noted that before as well, that d0 beta equals 0 whenever beta is non-zero. Now, some properties of the DDT, if you think about it, we are going to have we already proved this, that every integer, every entry in D is a non-negative even integer between 0 and 2 to the n. Always the top left entry of D is going to be 2 to the n. And the first row is always going to consist of all zeros except for that first entry of 2 to the n. Now, if S is 1 to 1, then you can say something about the first column, that it also will contain all zeros except for the first entry being 2 to the n. But that's only if S is 1 to 1. Also, the sum of the entries of each row has to be 2 to the n. And if S is bijective, then every row and every column of the DDT add up to 2 to the n. Now, let's relate the DDT to probabilities. When analyzing a block cipher for vulnerabilities, we often want to translate our results from the DDT into probabilities. The values from the DDT will be integers, but probabilities are values between 0 and 1. Let's just recall in probability theory, if we have a fixed finite set omega, then, and we call that the universe, then subsets E of omega are called events. And the probability P that an event E occurs is just defined in this case to be the quotient of the cardinalities of those sets. So the probability P is the cardinality of E divided by the cardinality of omega. And that gives a number between 0 and 1. So in our case, the universe, omega, is the difference set, delta sub alpha. And the event E is being inside the difference set, delta sub alpha comma beta. And what is the cardinality of our universe then? Well, it's the size of the difference set, which is 2 to the n. In our notation, the cardinality of the event E is the d alpha beta integer. So we can get a little formula for the probability associated to the event delta alpha beta. We call that P alpha beta. It's just the quotient of those cardinalities, which is d alpha beta over 2 to the n. Now, another way to look at it is we can just regard the universe, omega, as the set F2n, which also has a cardinality of 2 to the n. And the event E is the set of all x in F2n, such that S of x plus alpha equals beta. That's according to that little proposition that we talked about. That's another way to think about it. Gives the same thing. Now that we know what the definition of the differential distribution table is, let's calculate the DDT of a general linear S-box. Let's recall that a S-box L from F2n to F2m is said to be linear if for every elements x1 and x2 and f2n, that L of x1 plus x2 is equal to L of x1 plus L of x2. So L is an additive function. If we take any linear S-box L, then the different sets of L are actually easy to calculate, and we can find their cardinalities. The different set of L with respect to alpha and beta is equal to either the different set of alpha or it's equal to the empty set. It's actually equal to the empty set most of the time. Whenever beta is not equal to L of alpha, then the different set of alpha and beta is empty. But in the case when beta is equal to L of alpha, the different set of alpha and beta is just delta alpha, the different set of alpha. And therefore, d alpha beta is just the cardinalities of those sets. The cardinality of delta alpha is 2 to the n, and that happens when beta equals L of alpha. And it's 0 when beta is not equal to L of alpha. And that gives the values of the differential distribution table. We can look at this as saying that every row of the Ddt of a linear S-box contains all zeros, except there's a single entry, which is 2 to the n. And we can prove that easily. Just take alpha to be any element of f2n, and imagine we take a pair x1, x2 inside the different set of alpha. And remember, that just means that x1 plus x2 is equal to alpha. And then what is the difference of their images? What is L of x1 plus L of x2? Well, by the linearity of L, that's equal to L of x1 plus x2. But x1 plus x2 is alpha, so that's equal to L of alpha. So we see that L of x1 plus L of x2 is always equal to L of alpha. So that means x1 comma x2 is in delta alpha beta if and only if beta is equal to L of alpha. And the proposition follows. In the context of probabilities, this states that P alpha beta is either 1 or 0. It's 1 if beta equals L of alpha, and it's 0 if beta is not equal to L of alpha. And so what this really means is the Ddt of a linear S-box is not very interesting, because every entry is either as small as possible, which is 0, or as large as possible, 2 to the n. Now, when we talk about finding vulnerabilities in block ciphers by analyzing the Ddt, we mean that we look at the Ddts only in the nonlinear layer. So although the Ddt of this linear S-box does contain large values, like 2 to the n, which is as large as it gets, it doesn't mean that a cipher that uses a linear S-box is vulnerable. When we look at the Ddts of S-boxes for vulnerabilities in the block ciphers, we only look at the S-boxes that are in the nonlinear layer, the confusion layer. Now why don't we take a look at the Ddt of the XOR S-box. If we fix an element k in f2n, we can define a bijective S-box S from f2n to f2n, and we just define it as S of x equals x plus k. And notice when the key is non-zero that S of x1 plus x2 is not equal to S of x1 plus S of x2. So that means when k is non-zero, this S-box is not linear. So this is a different S-box than we just looked at. And we can ask ourselves, what is the Ddt of this S-box? Well, let's consider that equation, S of x plus alpha equals beta. And if we use the definition of S on that, we get x plus k plus x plus alpha plus k equals beta. We know x plus x is 0 and k plus k is 0. So this equation is equivalent to alpha equals beta. And right away, we understand the difference sets. Delta alpha beta is just going to be delta alpha when alpha equals beta and empty otherwise. And that means the corresponding cardinalities there, d alpha beta, it's either 2 to the n or 0. It's 2 to the n when alpha is equal to beta and 0 otherwise. And those are the entries of the table of the Ddt of this S-box. When alpha equals beta, that means the entry is located on the main diagonal. So this Ddt is going to look like 2 to the n located on the main diagonal and then zeros everywhere else. Now again, we see a large value 2 to the n in the differential distribution table. Since the key mixing layer is separate from the nonlinear layer, we shouldn't be concerned about seeing large values in the Ddt of the XOR S-box. Now let's take a look at writing some code that will calculate the Ddt of any S-box. To start, I think it'd be nice to create a 2D list all initialized with zeros, let's say with n rows and m columns, you would think that you could write something like this: A equals 0 times m times n, but that doesn't work. And we have to use this construction here, 0 times m, and then we just range over a loop. Notice the index I, the variable I there, doesn't do anything. So I think one convention in Python is, if that's the case, we just replace I with an underscore to denote, to indicate to people that the variable is not doing anything in the loop. The underscore is a valid variable name in Python. So in our case, we would like the number of rows to be 2 to the n and the number of columns to be 2 to the m. So those are the values we use inside our code, and we'll use capital D to denote the differential distribution table. And then, like I said, we'll change the I to an underscore. I just wanted to mention that line of code because it looks kind of confusing. So here's the code to generate the values of the DDT of any S-box. The way we're given an S-box is just as a list of its integer output. So if S has n input bits and m output bits, then S can be given as a list of 2 to the n integers. And that's how we think of S in this situation here. So we'll call our function DDT. It'll take in the S-box and the number of input and output bits. We'll define that empty 2D list, all initialized with zeros. And then we'll just range alpha from 0 to 2 to the n minus 1. And then for every x between 0 to 2 to the n minus 1, we just calculate beta as s of x plus s of x plus alpha. And then we have found a solution to that equation, and we increment d alpha beta by 1. And then after we finish looping over all those alpha and x, we'll have our differential distribution table D, and we just return it. Now, if you want to just print out the differential distribution table to the console, you can. It's easy. We just can use this code here. We just do a very small amount of formatting there, just so everything's lined up nicely. But one problem with this is that the differential distribution table can be quite large. For example, in a little bit in the video, we're going to look at the differential distribution table of the Rijndael S-Box. And it has 8 bits as input and 8 bits as output. So that means it's going to be a table that's 256 by 256 entries. And this is going to be too hard to view in a console. So we would like to also have some code that will print the DDT to a text file so we can look at it and see what it is. So here's the code that'll do that. Let's not worry about it too much right now. We'll take a look at it later and talk about it. But this is not too much different than what the code was on the previous slide. We just add a little bit of formatting here to make things look a little bit nicer. And we'll see how this works in a second with some real-world S-boxes. Before we look at the code, why don't we just talk briefly about the S-boxes that are found in DES, the data encryption standard. DES has 8 S-boxes, usually denoted S1 up to S8. And each one of the S-boxes there, SI, goes from F26 to F24. So it has 6 input bits and 4 output bits. So it's not bijective. It's not going to be one-to-one. Now, their differential distribution tables will therefore have 2 to the 6, which equals 64 rows, and 2 to the 4, which equals 16 columns. This differential distribution table is not too big, and we could print it out in the console window and we could see it. So we'll see that as well. In this book here, Differential Cryptanalysis of the Data Encryption Standard, the authors describe an attack, a differential cryptanalysis attack on the data encryption standard. And in Appendix B here, they define the difference distribution tables, which is what we're calling the differential distribution tables, same thing as the DDTs. And you can read their definition of what it is right here. It's the same as ours. And here's the first of 8 tables they provide. This is the DDT table for S1, for the data encryption standard. And we're going to see how our code can reproduce this table. One thing to notice is we have our number 64 in the upper left corner. That's 2 to the 6. We expect that. We expect all those zeros in the top row there. But we notice that we have some large values in this table. We see numbers like 12 and 14. And The associated probability to 14, say, is 14 out of 64, which is kind of large. This could be a sign that DES is vulnerable to an attack by differential cryptanalysis, and that is the topic of the book. Now, we can reproduce any of these DDTs with our code. I did a video about the S-boxes of DES and implementing them. One thing to notice is that the usual documentation for DES doesn't have the S-box listed as a list of output values. It uses a different technique, and I talk about that in that video. But in that video, I also show how to rewrite the S-boxes of DES just as a list of their outputs. And this is actually what we want to use for our code. All right, let's look at the code we talked about before now. Let's just start off with those first two functions. The first one is the DDT function, which just calculates the DDT as a 2D list of non-negative integers. And then the second function, print DDT, is just a way of printing the DDT to a console with a minimal amount of formatting. Why don't we try to print off the DDT of the first S-box of DES, S1. If we go to my GitHub page here and we look in the repository data encryption standard, we'll see some files here. Let's look under DES S-Box direct lookup. And here we have the format of the S-Box that we need. So if we want to reproduce the table that we saw in that book, we'll take the values of the first S-Box S1 and copy them. And then let's call print DDT for this list. And remember, it has 6 input bits and 4 output bits. And there it is. That is the same numbers that we saw in that book. Notice that 16 columns and 64 rows. Now there's no formatting, there's no headers for the columns, and there's no headers for the rows. And we'll see in a second how if we use the next function, printing it to a file, where all of that stuff is included. And that's the only reason it looks a little bit more complicated. So let's try to do that right now. Let's paste in that other function we talked about there. There it is. And why don't we try to call this function on this S-box S1. Now, when we do that, it'll look like nothing happened, but really what happened was a text file was produced in the same directory that the code file is in. So why don't we look at that text file? And here it is. Notice we have the column headers here, they're in hex, and we have the row headers, they're also in hex. Since S1 has 6 input bits, and 2 to the 6 is 64, our row indices should go from 0 to 63, and 3F is 63. And since there's 4 output bits, our columns should go from 0 up to 2 to the 4 minus 1, which is 15, and that's F. And we have 64 in the top left corner there, and then all zeros. So notice the integers inside the table, they're not in hex, they're just in normal base 10. But the headers on the columns and the rows, they're in hex. And that just makes it a little bit easier to read. And that's just the standard way of writing it. So this is how we can reproduce that table from that book. Now the last DDT we're going to calculate in this video is the DDT of the Rijndael S-Box. It's 8-bit to 8-bit, and it's the S-Box that's used in the Advanced Encryption Standard, AES. I did a video on that explaining its construction. But really the only thing we need is a listing of the values of the Rijndael S-Box. We don't have to understand the meaning behind it or how it's constructed. One thing to note though, the DDT of the Rijndael S-Box is going to be quite large because it's going to have 2 to the 8, which is 256 rows and 256 columns. So printing that out to the console would be too hard to read, and we'll want to use that function which prints it out to a text file. So here's the listing of the 256 values of the Rijndael S-Box. Now, it's obvious, but I'll just say it anyways, this is not the DDT. This is just the listing of the outputs of the S-Box, which will be a parameter, a function parameter, when we call the Ddt function. Let's paste those in here. And then we call the function that will print the Ddt of the Rijndael S-Box to a text file. And this will be quite large. It'll be 256 columns by 256 rows, but it's not that big. So again, when we call our function here, it looks like nothing happens, but really a text file is produced, and it actually overwrites the previous one. You could change that if you adjust the code a little bit. So let's look at that file. And here it is. It actually doesn't look that good, but word wrap is on. So why don't we turn that off? And there we go. So our row and column headers, they should go from 0 up to 2 to the 8 minus 1, which is 255, which is FF. So we expect our row and column headers to go from 0 to FF. And if we go all the way over, we see that it does end in FF. And if we go all the way down and all the way to the left, FF, yeah. So that's our table. And one thing to notice, of course, we have 2 to the power of 8 in this upper corner, all zeros in this row, all zeros in this column because it's 1 to 1, it's even a bijection. And then for every other row and column, except for the first row and first column, we have lots of zeros, we have lots of 2s, and the interesting thing is there's a 4. In every single row and column, except for the first ones, there's always a single 4. And the next thing we notice is that 4 is as big as it gets. The largest value in this table is a 4. That's quite a bit different than the DDTs of the Ddt S-Box, which was, we found values quite large, like 14. Let's just summarize in a proposition what we've seen about the DDT of the Rijndael S-Box. As we said, the DDT, D, has 256 rows and 256 columns. The only entries are actually 0, 2, 4, and 256. The first row in the first column of D is all zeros except for the upper left corner. The very first entry was just 256. And that's actually the only time 256 appears in the whole table. The rest of the entries are either 0, 2, or 4. Then the important result is that if we take any row or column except for the very first row and the very first column, we can say the following. In that row or that column, there's exactly one entry that's a 4. Also, there are 126 entries which are 2 and 129 entries which are 0. We see that the values d alpha beta of the Rijndael S-Box are actually very small. Other than that one in the upper left corner, 256, all the entries of the Rijndael S-Box are either 0, 2, or 4. And if we take the largest one, which is 4, the associated probability is 4 over 2 to the 8, which is 4 over 256, which is around 0.016. And that's pretty small, especially when we compare it to the probability that we saw with the S-Box from Ddt there, which had a probability of 14 over 64, which is 0.219, which is considerably larger than the probability in the AES S-Box, Rijndael. So this might be a sign that AES may not be vulnerable to an attack by differential cryptanalysis, whereas the DES cipher may be vulnerable to an attack by differential cryptanalysis. All right, that's the end of the video. Thanks for watching.